In April of 2023, a spacecraft belonging to the European Space Agency noticed something ordinary flicker across the sky. A distant star, briefly, almost imperceptibly, growing brighter. Nothing about the event looked unusual enough to make headlines. Stars flicker for all kinds of mundane reasons, and this particular brightening was catalogued, logged, and largely set aside. Nobody realized, at the time, that hidden inside that faint pulse of light was a planet, sitting roughly 40,000 light-years from Earth, on the far side of a significant portion of our own galaxy. And nobody realized that the instrument capable of actually revealing it was never designed to find planets that way or that far away at all. It would take more than 2 years, a second spacecraft that happened to be looking in exactly the right direction at exactly the right moment, and a graduate student willing to dig back through years of archived data before anyone understood what had actually been captured. This is the story of Gaia 23 Bra B, the most distant planet ever found by NASA's TESS mission, discovered almost entirely by accident, using a method the spacecraft's own designers never expected it to use. To understand why this discovery is so strange, you first need to understand what TESS actually is, and more importantly, what it was built to do. TESS stands for the Transiting Exoplanet Survey Satellite, and since its launch in 2018, it has become one of the most successful planet hunting missions in NASA's history, credited with discovering more than 800 confirmed planets to date. It works using a method called the transit technique. TESS stares continuously at wide patches of sky, watching thousands of stars at once for the tiny, telltale dimming that happens when a planet passes directly in front of its host star from our point of view, blocking a small fraction of that star's light for a few hours at a time. Do that repeatedly on a predictable schedule, and you have strong evidence of a planet in orbit. But the transit method has an important built-in limitation. It only reveals planets orbiting relatively nearby, relatively bright stars, ones close enough and clear enough for TESS's cameras to detect that subtle dimming with confidence. In practice, that means TESS's usual hunting ground extends out to roughly 150 light-years from Earth, a respectable distance by human standards, but a genuinely tiny sliver of our galaxy, which stretches across more than 100,000 light-years from end to end. Every planet TESS was ever expected to find was supposed to come from within that relatively local neighborhood. Gaia 23 b broke that expectation by a staggering margin. According to the research team's published findings, the planet's host star sits nearly 40,000 light-years from Earth, more than 250 times farther away than the outer edge of TESS's intended search radius. It is, by a wide margin, the most distant planet TESS has ever detected, found using a technique that has nothing to do with the transit method the spacecraft was actually built around. That technique is called gravitational microlensing, and it depends on one of the strangest, most elegant predictions to come out of Albert Einstein's general theory of relativity. According to that theory, mass bends the fabric of space itself, and light traveling near a massive object gets bent along with it. Under the right circumstances, if a foreground star happens to pass almost perfectly in front of a much more distant background star, from Earth's specific point of view, the foreground star's gravity can act like a natural lens, bending and magnifying the background star's light temporarily, making it appear noticeably brighter for a period of days or weeks before fading back to normal. If that foreground star happens to have a planet orbiting it, the planet's own smaller gravitational field adds an additional, much briefer ripple on top of the main brightening event, a secondary blip in the light curve that can reveal the planet's presence even though nobody could ever see the planet directly. This effect is exceedingly rare from any single vantage point in the galaxy because it requires an almost perfect chance alignment between two entirely unrelated stars, one nearby acting as the lens, and one much farther away serving as the background light source being magnified. It also happens only once, briefly, and never repeats for that particular alignment, since both stars are constantly moving relative to each other and to Earth. Unlike the transit method, which can be confirmed by watching the same dimming happen again and again on a predictable schedule, a microlensing event is a one-time only opportunity. Miss the window and the chance is gone forever. That is exactly what happened in April 2023, when the European Space Agency's Gaia spacecraft, a mission designed to map the precise positions and movements of more than 1 billion stars across the Milky Way, detected a brief, unexpected brightening in one particular patch of sky. Gaia recorded the event, consistent with a microlensing signal, but its own observing schedule for that region of sky was simply too sparse, too infrequent, to properly capture the finer details of the light curve. It caught the broad strokes of the brightening, but not the kind of dense, continuous coverage needed to tease out a smaller secondary signal from a planet, if one happened to be there at all. Then, purely by coincidence, less than a month later, NASA's TESS spacecraft happened to be pointed at that exact same patch of sky as part of its routine, ongoing survey of the wider heavens. TESS was not looking for a microlensing event. It was not searching for anything unusual at all in that particular direction. It was simply doing its job, continuously monitoring stars for transits, the way it always does. But because TESS happened to be watching that region with much denser, more frequent time coverage than Gaia had managed, its data captured something Gaia's own observations could not. Extra, subtle features layered on top of the main brightening curve. Exactly the kind of secondary signal a planet would be expected to leave behind. It is worth appreciating just how different Gaia's own mission is from TESS's, since the contrast helps explain why neither telescope could have made this discovery entirely on its own. Gaia was never built to hunt for planets directly. Its primary task is far broader, precisely measuring the positions, distances, and motions of more than 1 billion stars scattered across the Milky Way, essentially building the most detailed three-dimensional map of our galaxy ever assembled. To accomplish that enormous task across the entire sky, Gaia has to spread its observing time thin, revisiting any single patch of sky only occasionally, sometimes with gaps of days or weeks between successive observations of the same stars. That strategy works beautifully for large-scale galactic cartography, but it is exactly the wrong kind of coverage for catching the fine details of a brief microlensing event, which can rise and fall meaningfully within a matter of hours or days. TESS's observing strategy is almost the opposite. Built specifically to catch short transit dips lasting just a few hours, it stares at the same patches of sky with dramatically more frequent, near-continuous coverage, checking in on the same stars again and again over a period of weeks. That difference in cadence, thin and broad for Gaia, dense and narrow for TESS, turned out to be exactly the combination needed to catch both the overall brightening event and the finer secondary ripple hidden inside it. Nobody noticed any of this at the time. The data simply sat archived. One small, unremarkable event buried among years of TESS observations, covering enormous swaths of the sky. It took a dedicated researcher, years later, deliberately going back through old microlensing candidates flagged by Gaia, cross-referencing them against TESS's own archives, to finally connect the two datasets and realize that TESS had, completely by accident, captured evidence of an actual planet. The researcher was Mallory Harris, a doctoral candidate at the University of New Mexico, working alongside her advisor, Diana Dragomir, a professor in the same department. Their analysis, published on July 1st, 2026, in the journal The Astrophysical Journal Letters, confirmed that the signal buried inside TESS's archived data really did represent a planet, one now officially named Gaia 23 Bira b, in honor of the original Gaia detection that first flagged the event. The planet itself turned out to be a super Jupiter, a gas giant considerably larger than Jupiter, orbiting an orange dwarf star roughly 80% the mass of our own Sun. Its orbit sits at a distance from its host star, comparable to Jupiter's own distance from the Sun, meaning this is not one of the tightly packed, scorching hot worlds TESS usually finds through the transit method, which favors planets orbiting close to their stars, where transits happen frequently and predictably. Gaia 23 Bra b sits much farther out. In a kind of orbital neighborhood, the transit method is fundamentally bad at detecting. Precisely the kind of world microlensing is uniquely suited to reveal instead. As Diana Dragomir put it in NASA's official statement announcing the discovery, when TESS first launched, absolutely nobody expected it would ever be capable of finding a planet this way. The spacecraft's cameras, its data pipeline, its entire observing strategy, all of it was designed around the transit method and nearby stars. Detecting a distant microlensing signal was never part of the plan. And yet, purely because TESS happened to be pointed in the right direction at the right moment, capturing continuous high-cadence data, the way it always does, regardless of what happens to pass through its field of view, it stumbled into evidence of a planet 40,000 light-years away, a discovery method its own designers never anticipated. One science writer covering the story offered a fitting comparison. It is a bit like pointing an ordinary backyard bird camera at a bird feeder in your garden, only to later discover, buried somewhere in months of footage, that you had also accidentally captured wildlife roaming on another continent entirely. Out of more than 6,000 confirmed exoplanets discovered to date, roughly 3/4 were found using the transit method, the same technique responsible for the vast majority of TESS's own catalog. Microlensing, by contrast, accounts for less than 5% of all confirmed exoplanet discoveries, largely because it depends on rare, one-time chance alignments rather than a repeatable, predictable signal. The two methods are, in a real sense, complementary rather than competing. Transits are extremely good at revealing planets that orbit close to their stars, tightly packed worlds that block a measurable fraction of starlight on a short, predictable cycle. Microlensing, on the other hand, is far better suited to detecting planets that orbit much farther from their host stars, including worlds sitting in the same general kind of habitable zone distance our own Earth occupies, or even farther out still, precisely the kinds of planets the transit method tends to miss almost entirely. As Dragomir explained, transits and microlensing reveal genuinely different categories of planet, and offer genuinely different kinds of information about the worlds they find. Transits reveal a planet's physical size directly, and when combined with other techniques, can also help pin down its mass and overall density. Microlensing works differently, revealing a planet's mass and its orbital distance from its star, information astronomers would otherwise have essentially no way of obtaining for a planet sitting tens of thousands of light years away, far too distant and far too faint for almost any other detection method currently available. Mallory Harris has emphasized one particular advantage microlensing holds over the transit method, one directly relevant to the ongoing search for potentially habitable worlds. Planets that orbit extremely close to their host stars, the kind the transit method finds most easily, tend to blend into the star's own gravitational influence in ways that make them difficult to distinguish clearly through microlensing, since their signal gets overwhelmed by their star's much larger mass. Planets sitting farther out, at distances comparable to where Earth orbits the Sun, or even farther still, produce a much cleaner, more distinct microlensing signal instead. That means microlensing is uniquely well suited to finding exactly the kinds of worlds most likely to sit within a star's habitable zone, the region where conditions might allow liquid water to exist on a planet's surface, precisely the category of world. The transit method is comparatively weak at detecting in the first place. The implications of this discovery go beyond a single unusual data point as well. If TESS managed to accidentally capture one microlensing planet signal buried unnoticed for years inside its own archived data, researchers now strongly suspect there are almost certainly more such signals hiding in TESS's records, simply because nobody had previously thought to search for them using this particular method. TESS has been continuously observing large portions of the sky since 2018, accumulating roughly 8 years of archived data by the time this discovery was finally confirmed. Somewhere inside that enormous archive, other brief, easily overlooked microlensing signals may be sitting quietly, waiting for someone to go looking for them the way Harris and Dragomir's team finally did. That realization connects directly to an even bigger mission still to come. NASA's Nancy Grace Roman Space Telescope, on track for launch in the fall of 2026, is specifically designed to use microlensing as one of its primary observational strategies, rather than stumbling into it by accident the way TESS did. Roman will spend part of its mission staring directly at the crowded, star-dense center of our own galaxy, an area packed with far more potential foreground and background star pairs than TESS ever surveys, dramatically increasing the odds of catching genuine microlensing events in progress. According to NASA's own projections, Roman's dedicated microlensing survey is expected to reveal roughly 1,000 new microlensing planets over the course of the mission, alongside an estimated 100,000 additional planets, detected through the more traditional transit method elsewhere in its broader survey. Michael Fausnow, a professor at Texas Tech University involved in analyzing the TSS discovery, described Gaia 23 Bra B as something like an early preview of exactly the kind of science Roman is specifically being built to deliver at a much larger scale. TESS's accidental detection essentially serves as a proof of concept, a demonstration that this exact combination of a wide-field survey, like Gaia, flagging a candidate event, followed by denser, more detailed follow-up observations from a second instrument, can genuinely reveal planets that neither telescope alone would ever have caught unassisted. Roman itself represents a fundamentally different design philosophy than either Gaia or TESS. Rather than splitting its attention across the entire sky the way Gaia does, or scanning wide, rotating patches of sky in the systematic pattern TESS follows, Roman's dedicated microlensing survey will instead stare fixedly at a single, extremely crowded region near the center of the Milky Way for extended stretches of time, an area containing an enormous concentration of stars packed closely together along our line of sight. That crowding dramatically increases the raw odds of catching a genuine chance alignment between a foreground and background star at any given moment, essentially trading Gaia's all-sky coverage and TESS's incidental follow-up for a deliberately engineered environment where microlensing events should occur far more frequently and predictably than anywhere else astronomers have systematically searched before. There is also something worth appreciating about just how narrow the window for this particular discovery really was. Gravitational microlensing events, by their very nature, do not repeat. The specific alignment between the foreground star and the background star responsible for Gaia 23 Bra B's detection happened once, played out over a matter of weeks, and then ended permanently as both stars continued along their own separate paths through the galaxy. If TESS had not happened to be aimed at that exact patch of sky during that exact narrow window in 2023, the additional data needed to confirm the planet's existence would never have been collected at all, and this discovery simply would not exist. There is no way to go back and re-observe the event. There is no way to schedule a follow-up. Whatever data happened to be collected during that brief overlap between Gaia's detection and TESS's own routine observations is the only evidence of Gaia 23 Bra B that will ever exist. That underlying fragility is part of what makes microlensing such a demanding, unusual technique, compared to more conventional planet hunting methods. Researchers cannot simply decide to study a specific microlensing planet in more detail later, the way they might schedule additional transit observations of an already confirmed world. Once the alignment passes, the opportunity is gone permanently, leaving behind only whatever data happened to be captured during that narrow, unrepeatable window. As Mallory Harris has pointed out, this makes detailed follow-up observations of any individual microlensing planet extremely difficult, since there is no second chance to look again. But it also makes the method valuable in a completely different way, functioning less as a tool for studying individual planets in depth and more as a broad demographic survey, revealing general patterns about how common certain kinds of planets are across large stretches of the galaxy, based purely on statistics gathered from many brief, one-time events collected over the years. Gaia 23, Bar AB's discovery, is also notable for another reason entirely. It stands as one of only a small handful of microlensing planets ever confirmed using data gathered from space-based telescopes, rather than the ground-based observatories that have historically dominated this particular field of research. That makes it an unusually important test case for the Roman Space Telescope's own upcoming microlensing survey, offering researchers a genuine, already confirmed example of exactly the kind of signal Roman's instruments will need to identify reliably once its full survey campaign begins in earnest. Step back from the specific technical details, and the deeper story here becomes almost quietly remarkable. A spacecraft built and launched with one very specific job, watching relatively nearby stars for the subtle dimming caused by orbiting planets, ended up accidentally capturing evidence of a completely different kind of world, sitting so far away that its host star's light had already been traveling toward Earth for roughly 40,000 years before TESS ever recorded that brief, easily overlooked flicker. Nobody built TESS expecting it to reach that far. Nobody designed its survey strategy with galactic microlensing in mind. And yet, because it simply kept doing its normal job, continuously, faithfully, without any special modification, it happened to be in exactly the right place, pointed in exactly the right direction, at exactly the right moment to catch something. Nobody thought it was capable of catching at all. Somewhere out there, roughly 40,000 light-years away, a super-Jupiter continues its slow, distant orbit around an orange dwarf star, entirely unaware that its brief gravitational fingerprint was accidentally captured by a spacecraft never designed to notice it, then rediscovered years later by a graduate student patient enough to go looking through data nobody else thought to check. And somewhere inside 8 years of TESS's own archived observations, researchers now strongly suspect other planets exactly like it may still be waiting quietly to be found, hidden not because the data doesn't exist, but simply because nobody has yet thought to look for that particular kind of signal in that particular corner of the archive. There is a genuinely humbling lesson buried in that fact. Modern astronomy increasingly depends not only on building bigger, more powerful telescopes, but on returning patiently to data that has already been collected, sometimes years earlier, and asking new questions of it that nobody thought to ask the first time around. TESS did not need any new hardware, any new mission extension, or any new funding to make this discovery. It only needed someone willing to look at old observations through a completely different lens, quite literally, than the one the spacecraft was originally built around. If you want more real discoveries from the true edges of what our telescopes can actually see, subscribe and stay with us, because the next hidden planet might already be sitting inside data we collected years ago, waiting for someone to finally notice it.